Assalamualaikum everyone. Welcome back to Easy Taleem. In the previous lecture, we learned something extremely important. Whenever differentiation used the chain rule, so if we used chain rule in differentiation, right, in order to reverse that in integration, we usually do substitution. Okay, integration by substitution. Today, we are dealing with a completely different family of questions. Look at these three integrals. Let me write it down for you. So if I ask you to integrate x times e to the power of x with respect to x, how are you going to do it? What if I give you another question? Integrate x multiplied by sine x dx. How are you going to do it? What is the integral of ln x with respect to x? Now, none of them can be solved using substitution. Why? Because they were never created by chain rule, right? You can see that this was not created by chain rule. This is not the differential of this, right? Similarly, this is not the differential of the argument of sine x, and we don't have anything here, right? So therefore, they were created by another differentiation rule. Which one exactly? That's the product rule. Okay, so because they were created using product rule, we are going to undo it using a technique called integration by parts. Now, this is something I wish somebody had taught me when I was learning calculus, that you must recognize the structures before you calculate, right? Before trying to integrate, don't ask which formula do I remember. Ask which differentiation rule must have created this expression, okay? And if you can answer that, half the problem is already solved. Now, if it was power rule that created it, right? You use integration technique of by parts, and if chain rule must have created that, you use integration by substitution. Okay, sorry, not power rule, it's the product rule, right? Integration by parts. And if it's the power rule, then you undo it in integration by simple integration or simple reversal of power rule. Okay, simple reversal. Now, that is how mathematicians think, not by memorizing pages of formulas, but by recognizing the structure. Now, let's discover the formula. Forget everything that you've memorized so far. Let's derive it ourselves. You start with something you already know, which is the product rule. So now, what is the product rule? If you have got two functions multiplying together, let's say u is a function of x and v is another function of x, and they are multiplying together, right? So u times v is y, right? Now, in order to find dy by dx, it is u v dash, which is dv by dx, plus v u dash, which is du by dx. That's the product rule, right? Everyone knows this. So now let's rearrange it. So we can move one term. Let's say we can do, or how do we do it? Okay, so what we can do is I can okay, let me first of all change the color in order to create some distinctions. This y may be written as u times v. So d upon dx of u times v is same as u dv by dx plus v du by dx. So now I can take this one here. So I'm going to have d upon dx of uv minus v du upon dx is equal to u dv by dx, right? That's simple. Now we must integrate every term. Now watch carefully. What if I put the integral sign? I will use another color in order to create this distinction. Let's use green. So now let's put dx here, and let's put dx here. So the middle integral disappears. Why? Because this we have here. So this one is going to become uv, right? This is uv, and this becomes wait. Okay, yeah, so this is pretty straightforward. Let me just clean it up. So this term is going to become u dv, right? U dv, and you put an integral sign here, and this terms becomes u v, and this terms become integral of v du, right? So uv minus integral of v du is equal to integral of u dv. This formula is called integration by parts. Okay, and we are going to do a lot of practice of it in this very lecture, so you're going to understand it properly, so don't worry. Now, derivation is not part of your syllabus, but I just tried to show it to you so that you do understand that why do we do what we do. Okay, now we didn't memorize this, we memorized it, we derived it, and so if you ever forget it in an exam, derive it again. It takes just 30 seconds, right? You just undo the product rule and make u dv the subject, right? Now, so which function becomes u? So now comes the real skill. So u and dv. So what is u going to be equal to and what is dv going to be equal to, right? There is no point knowing the formula. Now, by the way, do you see that we have a product of u and dv, right? And here, this v is the integral of dv, and this and this one is, sorry, wait a second, and this one is going to be v du, right? Okay, let's do it now. So how do we choose u and how do we choose dv? There's no point knowing the formula, so here we introduce LIATE. This is for inverse, this is for logarithm, this is for algebra, this is for trigonometry, and this is for exponential, right? Now, let me put it here. So whichever comes first in this, you choose that to be u. So for example, if you had x times exponential x, right? So if you had to integrate it, so this is going to become dv, this is going to become dv, and x is going to become u. So this is dv and this is u. So you will say that u is equal to x and dv is equal to exponential of x. So now we need a du here. So du is going to be what? Du is going to be 1, and we need a v here as well, right? So here is a v and here is a v, right? So v is going to be equal to, so integral of exponential, sorry, what happened? Integral of exponential is nothing but itself, right? So now the formula is what? It is u times v. So we are multiplying this with this. So I'm going to write x times exponential of x, and then there's a minus integral, and then we have v du. So we multiply it together. So this is going to become exponential, and we put a dx, and this is the integral of x ex dx. Okay, so can you see that this is going to become x ex minus integral of ex is nothing but ex, and there's going to be a constant of integration, and that's the integral of x ex dx, and that's it. So you can reverse the process, you can find the differential of it, and you will see that that's going to be exactly the same. Okay, how do you differentiate it? You apply the product rule here, you let it be as it is. So okay, so let me just do it for you. Okay, let me use another color. So uv dash, so this is going to become u v dash plus v u dash minus the differential of this plus the differential of this, which is this. So this and this gets cancelled, and you are left with x ex, which is exactly the term that you have here. Okay, and that's it. So there are only two possibilities in this question. I'm just recapping it. Option 1 was that you take u as x, and option 2 was that you take u as ex, right? In this question, you could either take this as u or you could take this as u, right? In either case, the other one would be dv, right? Now, which one makes life easier? So if you take u, the derivative is going to become a constant, right? So that makes our life easier. So and you saw that this du appeared in the integral. So if it becomes a constant, then the life is easy, right? So hence we choose whatever creates a constant. You saw that this exponential, when gets integrated, it's again giving us an answer in a variable, right? So always choose a function whose derivative becomes simpler. So when you differentiate x, you get a 1. So very good. So and when you differentiate e to the power x, it's still e to the power x. So there was no simplification. Therefore it was better to use u as x, right, as we did here, and we chose dv as ex dx. Now this is the thinking process, no magic. So once you understand it, you can just apply the LIATE formula, and it's going to make your life easier. Now let's do another one. Which question did we write down? Okay, x times sine x. Let's do it. So if you're given, and I want you guys to pay close attention, x times sine x dx. Now this is going to become, again, you have a u, you have a dv. Now which one is going to become simpler? X is going to become simpler, so we take that as x, and du is going to become 1. And if dv is sine x, so v is going to become minus cos x, right? So that's going to become minus cos x, and the formula is uv minus integral of v du dx, right? So that's going to become, so uv is going to become uv, so minus x cos x, and then minus integral of v du. So v du is going to become negative cos x. So if there's a negative cos x here, I can remove this and put a plus here, and now this is going to become minus x cos x, and integral of cos x is just sine x, and then plus c. And now if you differentiate it, I'm just going to show you that you're going to have x sine x as the result. So this is going to become, so the differential of this is going to become the differential is going to become u v dash, which is minus sine x, u v dash plus v u dash, which is just 1, and then plus sine x. So this becomes x. Oh, sorry. The differential of sine x is nothing but cos x. So this becomes u v dash is minus sine x. So this is plus x sine x, and then this was minus cos x, and this is plus cos x. Okay, so you saw that we just landed back at x sine x, right? So that's easy. Now so always try to verify it, right? Just makes your life easier. Now how are you going to, let me surprise you guys, and I hope some of you who are watching it are able to find out the hidden technique for integration by parts, right? Now remember, we have LIATE, right? Now, but you are going to argue that there is only a logarithmic function here. I'm going to contest, right? There is another term attached to it, which is 1, and this is ln x dx. So now this ln x comes here, and this 1 is not exponential, it's not trigonometric, it's not inverse, it is algebraic term. So your 1 comes here, your log comes here. So u is going to become ln x, because you do understand that when you simplify it, you're going to get something very simple when you differentiate it. So du by dx is going to become 1 upon x, right? And dv is going to become 1, the differential of which is going to become x. So now the integral of it is uv, which is x ln x, minus integral of v du by dx, which is this times this. So this is nothing but 1. So this becomes x ln x minus x and plus c. And this is the integral of ln x. Okay, so it is as simple as that. And you can try to differentiate it back, and you will see that you're going to get ln x as the result, right? Now, this appears in Cambridge surprisingly often. Never panic, just remember that every function can be multiplied by 1, right? That's very easy. Now, how do you choose u quickly? That's the same formula that I did. I wrote LIATE, my bad. You should write LIATE. Inverse comes after logarithm. Okay, so always know that. Now, so this is simpler than this one. This one is simpler than algebraic. Algebraic is simpler than trigonometric, and trigonometric is simpler than exponential. Although exponential and trigonometric, they both never turn into a constant. So if you get something like ex multiplied by sine x, you're never going to have a constant term. You're never going to find a term where the product of two differential terms. Okay, I'll show you something. So if you have ex sine x and you have to integrate it with respect to x, let's call it I, right? Now you will see something. So let me take u as sine x. Let me take dv as exponential of x, and du by dx is going to become cosine of x, and v is going to become exponential x. Now you will see something. So this becomes uv, which is exponential x sine x, minus integral of exponential x cos x, right? And then again dx. So we are going to come back to do it. Now this is what? This again, we are going to apply the same integration by parts. So u is going to become cosine of x, du by dx is going to become of minus sine x, and dv is going to become of exponential of x, and v is going to become exponential x, right? So I'm going to copy it down as it is, which is exponential x sine x, and minus, now integration by parts, when I apply here, I first multiply this with this, so this becomes ex cosine of x, right? Minus integral of ex with minus sine x. So this is ex minus sine x. I'm going to bring this minus outside, so I get the same term, right? Now, if I take this as I can put this I here. So this is going to become exponential of x sine x minus exponential of x cos x, and this is going to become exponential of x sine x dx. Now you will see that this exponential of x sine x dx was what? It was I. So I, instead of this, I can rewrite minus I, and there's an I here, and this is exponential of x sine x minus exponential of x cos x, and I can take this here. So this becomes twice of integral is exponential of x sine x minus exponential of x cos x, and I can now take exponential of x common, and I can divide both the sides by 2. So the integral is going to be half ex, and this is going to become sine x minus cosine of x, and that's the integral of ex sine x dx. Okay, so LIATE is no magic. It's simply based on experience, right? Once you do math a lot of time, you do the calculus a lot of time, and then you realize that what happens here. Okay, now when does integration by parts happens? Twice, and this is what we did here, but this was a recurring thing, right? Now let's do where we must do it twice. So what if you have something like this? So you will see that when you take u as x squared, you still get a 2x here. Du by dx is going to become 2x, and dv is going to become exponential of x, and v is going to become exponential of x as well. So this is going to become x squared times exponential x, and then integral of ex times 2x. I will take 2 out, so this becomes xex, right? And dx. Now I apply this the second time, integration by parts the second time. So this becomes, so u is going to become x, dv by dx is going to become ex, and du by dx is going to become 1, and v is going to become exponential of x. So now this becomes xex minus integral of exponential of x dx, and now this becomes x squared exponential of x minus 2x exponential of x plus 2 integral of ex is just ex, and plus a constant of integration, right? So that's it. And you will see something. There's an x squared, and there's a minus 2x, and there's a plus 2. So this term is always one differential down, right? But and the sign also changes, right? However, let's not try to memorize stuff. I just want you guys to know this very well and just apply it perfectly. Now, so whenever there's an there's something inside there's a variable inside another integral, you apply parts again. Students often think they've made a mistake. No, some integrals naturally require repeated applications, and Cambridge likes such type of questions. Okay, not because they are difficult, but because they're testing your persistence, right? You're not losing heart, you're not thinking, you're not getting confused that whether you are doing it right or wrong. You must be confident in what you're doing, right? Because math always converge. If the process is right, then you should be confident about it. Okay, now what is the biggest examiner trap here? Students sometimes differentiate v instead of integrating it. So if you take something as dv here, you must take the integral of it. For example, if you had something like e to the power of 2x, then you must take it as e to the power of 2x upon 2, right? So that's a very important thing. Remember, you always differentiate u. So if u was x squared, du by dx is going to become 2x, right? Never reverse these jobs. One small mistake and your whole question is gone. And the best part is that you can always verify. If after you have obtained your answer in integration by parts, if you can reverse it in order to land at the same expression given in the question, then you have done the job right. Okay. Now, Cambridge gives you mixed questions. Let's try to combine everything. Let's say that Cambridge has given you a question which is integrate x plus 1 times e to the power of x and integrated with respect to x, right? So u is going to be algebraic in LIATE, which comes before exponential. So dv by dx is going to become exponential of x, and or rather I will put a 2x. So 2x, and v is going to become half e2x, and u is going to become x plus 1, and du by dx is going to become 1, right? Now, this 2 is the power, 2x is the power of exponential. So now the integral is going to be uv, which is nothing but half x plus 1 e power 2x minus integral of this times this. I can bring this half out, and this is e2x dx, and this is going to become half x plus 1 e power 2x minus 1 upon 4 e power 2x plus a constant of integration, and that's it. Okay? Don't rush. Expand your thinking. Choose u as x plus 1. You did not need to expand it. I mean, a lot of students will do this x e 2x dx plus integral of e 2x. I mean, there is no harm, but you could have just, you could have just taken this entire thing as x plus 1 like we did, right? Now, let's do a more interesting example here. Let's do x squared cos 2x and try to integrate it, right? I will change color for the solutions. So u is going to be x squared because algebraic appears before trigonometric in LIATE, right? So trigonometric is going to become cos of 2x, integral of which is going to become half sine of 2x, and du by dx is going to become 2x. And now you can see that we must apply integration by parts twice because you see a variable here and not a constant, right? You only stop after this becomes a constant, right? As you have seen by experience in these questions. So this becomes uv, which is nothing but half x squared sine 2x minus integral of, you multiply this with this, so 2 cancels with 2, so you get x sine 2x and dx. So now I'm going to copy the first term down as it is, which is half x squared sine of 2x, and then I'm going to apply integration by parts again, where my u is going to become x, and du, or I will just write u prime is equal to 1, and v prime is going to become sine of 2x, and v is going to become negative half cos of 2x, right? So this becomes negative half x cos of 2x minus integral of cos of 2x, negative cos of 2x, so I'll put a plus here, cos of 2x. So now this becomes, wait a second, so this becomes half x squared, let me just clean everything down, sine of 2x, this minus with this minus becomes a plus, plus half cos of 2x, this minus with this plus becomes a minus, minus half integral of cos 2x is sine 2x over 2, so sine 2x over 2 is, so this becomes 4, and then a constant of integration, and this right here is your answer. It is as simple as that. Notice something powerful. Today's lecture is using yesterday's or our last lecture substitution ideas inside integration by parts, what we did on Friday. So math isn't really separating chapters. It's one connected language. Okay, now how does an examiner think? Cambridge isn't impressed by students who memorize that u dv dx is going to be u v minus integral of v du with respect to x. I mean, it's okay if you're remembering this formula, but the thing that must be rewarded is students who recognize the structure. This integral came from the product rule or the power rule or the chain rule, right? So the decision comes first, the algebra or the calculus, it comes second, right? Now let's do a final challenge before the next part that we move on, which is trapezium rule and inverse trigonometry and all of that. So try these without pausing the lecture too early. I want you guys, or rather, yeah, just pause the lecture and try to do these integrals. X cube, EX, DX. These are from your Cambridge endorsed black cover book. X, ln x, dx. I mean, these are very straightforward questions. And this is x cos 3x dx. Okay. So if this feels difficult, it's fine. We'll revisit combinations like that in future mixed paper sessions. Or perhaps let me do this one just for you. Okay, so x ln x, LIATE, log appear before algebra, right? So I'm going to take u as ln x and I'm going to take dv as x, and this becomes u prime becomes 1 upon x and v becomes half x squared. Very simple. So now the integral becomes half x squared ln x minus integral of half x squared times 1 upon x. So that is half x dx. As simple as that. So this turns out to be half x squared ln x minus 1 upon 4 x squared plus c. That's it. So I hope you were able to see it as well. So in this section, we have learned something much bigger than a formula. We have learned that integration by parts is simply the product rule running backwards, right? So integration by parts has been derived from undoing the product rule, right? You saw it. So it is as simple as that. Also, once you see that connection, the formula becomes a consequence, not something to memorize, right? It was a consequence by undoing product rule, and that is what derived this formula. In the final part of this chapter that we are just going to do, we'll tackle the questions that separate good students from A star students, which I'm sure all of you are. We are going to do inverse trigonometric integrals, right? So how do you integrate this, right? How do you integrate sine inverse of x? We are going to do all of that. And higher powers of sine and cosine, such as what if I give you sine 5x dx? How are you going to do it? This is not a consequence of a chain rule, right? So you cannot use integration by substitution, right? We are going to do products of trigonometric functions. We are also going to do the trapezium rule, the numerical integration, mixed Cambridge numerical integration is nothing but trapezium rule. And then we are going to do some mixed Cambridge exam questions as well, and also learn to decide which integration technique to use in under 10 seconds, right? Now, so in the first part that we did on Friday last week, we dealt with substitution. Earlier in this lesson that we just concluded, we reversed the product rule using integration by parts, and now we are going to start to deal with the questions where students usually know the formulas but still do not know what to do first, right? So for example, if you have to integrate this, so you and sometimes so also this is another question. I mean, you have done trigonometry, but I will show you how to use that knowledge in order to do this. Also, what if I give you to integrate this, right? There's a quadratic factor in the denominator, right? You have done you have done partial fractions as well. You have done binomial as well. So we will use all that knowledge here. So, or maybe you may be asked to use a numerical method for this, and I'm going to discuss how to do that. The objective today is not to collect more formulas. It is to learn how to read the structure of an integral and make the correct first move. And this is what P3 teaches you, and how P3, and this is how P3 distinguishes itself from P1 or your O-level math or your ad math, right? Now, let's first do in part A. Let's first do higher powers of sine and cosine. So I'd like to start with this sine 5x dx. A lot of you will feel compelled to, write it down like sine x power 6 over 6 and divided by cosine of x. That's absolutely wrong. Don't do that. Don't do that. Okay. Now, so here I would like to rewrite it as sine x times sine x with power 4, right? And now I can see some similar structure here, right? I'm going to show you. Now, there is one technique that I want you guys to learn. Now, this you can rewrite it as, okay, I'll show you something. And I'm going to show you that why do we do it. So you can see that this can be written as sine squared of x squared further, right? Now, I can rewrite it as sine x times 1 minus cos squared x, right? The first identity, the circular identity, that cos square x plus sine square x is equal to 1. And then you further square it. Now you can see that I can find the differential of this here, right? So now I can take a substitution. I can take u as cos x. So u is equal to cos x, and du by dx is going to become minus sine x, right? Now see, so this becomes, so how do you do it further? So this is going to become minus sine x. So my dx is going to become minus du over sine x. Yeah, that's right. Okay. Now, this becomes sine x times 1 minus cos square x. So cos square x is going to be u square, 1 minus u square raised to the power of 2. And dx is going to become minus du over sine x. Can you see that we got rid of our trigonometric function and now everything is in terms of u, right? So now I can integrate it. This becomes 1 minus 2u squared plus u4 du, right? And there is a minus here as well. Or or I can put a minus here, positive here, and a minus here, right? So this now becomes minus u plus 2 upon 3 u cubed minus 1 upon 5 u power 5 plus c. And then you can plug the u back, right? So u is going to be equal to cosine of x. So minus cosine of x plus 2 upon 3 cosine cube of x minus 1 upon 5 cosine 5 of x and plus a constant of integration. And that's how you do it for odd powers, right? So this is the complete method. The key decision was not substitution. The key decision was save one sign, then convert the remaining even power. So you had a sine 5x. You converted into sine x times sine 4x. Now sine 4x is even power. You converted into sine squared x to the power of 2. Then sine squared x converted into 1 minus cos squared x. And now you took this u cos squared x as u, right? And that was the key decision. Now, when the power of sine is odd, so for example, sine has some power, sine to the power of 7x, right? Save one factor of sine x and then use 1 minus cos squared x for the remainder, right? Now, what if, now let's try to do it for cosine, odd powers of cos. Oh, okay, I do not need to remove it. We can move on. We are not saving papers here. Save the trees. Okay, now let's do it for cosine of 3x. Let's say. Now you do the same. You save one cos, so you get what? So this becomes cosine squared x times cos x dx, and this becomes cosine squared of x is going to become 1 minus sine squared x, right? And then there's a cosine of x here. So I'm going to write it here and dx. So now if I substitute u as sine x, so du by dx is going to become cosine of x, or dx is going to become du over cosine of x. So du over cosine of x. So this cancels this. So I'm left with 1, and this is, by the way, u squared. So 1 minus u squared du, right? Now this is very easy. This is just u minus 1/3 of u cubed plus c, and then u was sine x, sorry, u was sine x, so I'm going to write sine x minus 1/3 of sine cubed x plus a constant of integration, and that's it. Okay, same strategy, different trigonometric function. Now what if you have mixed odd powers? Now what if you have sine cubed x times cos 4x dx. Now the sine power is odd. As you can see, it's a 3. So you save one sine. So this becomes sine x times sine squared x times, right? And now you will convert this sine squared x into 1 minus cos squared x. So I will just write down 1 minus cos squared x, and then there's a cos 4x, right? And there's a dx, right? It is as simple as that. And now you take the substitution. So u is equal to cos x, and du by dx is going to become minus sine x, right? So this is going to become, so sine x I copy down as it is from here. This becomes 1 minus u squared, and this becomes u to the power of 4, and dx is going to become du over minus sine x, du over minus sine x. Sine x cancels sine x in the numerator and denominator. So I am now left with minus integral of u power 4 minus u power 6 du, and this is going to become minus 1 over 5, or rather I will put this minus and make this plus, right? So this becomes minus 1 over 5 u5 plus 1 over 7 u7, and plus constant of integration. U was cosine of x, so I'm going to write minus 1 5 cosine power 5x plus 1 upon 7 cosine power 7x plus a constant of integration, and that's it. It is as simple as that. Now what if both powers are odd? Okay, now let's see that if you have an integral of, let me change color, if you had to find out sine cubed x multiplied by cosine of 5x dx, you could save one sine or one cosine. It's totally up to you. Both methods work. I'm going to do it with one method, you have to do it with another one, right? But choose the route that leaves the simple algebra. For example, save one sine. So if I save one sine, this becomes sine x, and then sine squared x, which is 1 minus cos squared x, and this is going to become cosine of 5x, cosine power 5x dx. Now if I take the substitution, u is equal to cosine of x, du by dx is going to become negative sine of x. So now this is, so sine of x is going to get copied as it is. This becomes 1 minus u squared. This becomes u power 5, and dx is going to become du over minus sine x, and sine x is going to get cancelled, and you're left with integral of minus 1 minus u power 5 plus u power 7 and du, and this is going to become minus 1 over 6 u6 plus 1 over 8 u8, and there's a du and there's a constant of integration, and u was equal to cosine of x. So this is going to become negative 1 upon 6 cosine power 6x plus 1 upon 8 cosine power 8x, and a constant of integration, and that's it, right? Now let's try to do, in part B, let's try to do the even powers. So we have dealt with the odd powers. Wait a second. Okay, so there was some distraction on my end, so I had to deal with it. Okay, now, so what if in part B, let's try to deal with the even powers of sine and cosine. So if you had to integrate sine squared of x dx, now so neither power is odd, right? There is no spare sine or cosine to become du, so substitution is not the first move. Use the double angle identities. Now you do know that cosine of 2x is what? It is cos squared x. Sorry, so let me write it down properly. Okay, so cos of 2x is equal to cos squared x minus sine squared x, or we saw another one which was 2 cos squared x minus 1, or 1 minus 2 sine squared x, right? So you can open it up as 1 minus cos squared x and get this, or you could open it up and write down 1 minus sine squared x and get this, or you could open it up as 1 minus cos squared x and get this second one, right? So I have a sine squared x, so I can see that this the sine squared x may be rewritten as 1 minus cos 2x over 2, so half can be taken out. So now this is fairly simple. So this is half x minus sine 2x over 2, and then a constant of integration. So this becomes half x minus 1/4 of sine 2x plus a constant of integration. Very simple, right? Now, so what if you had cosine squared of x? right? Now, let me change color because it's another question. What if you had to integrate cosine squared x dx? Now, you can see that cosine squared x may be rewritten as by the same, you can go back and see that it could be rewritten as cos 2x 2 cos squared x minus 1. So cos 2x plus 1 over 2, right? So I can rewrite it as half 1 plus cosine of 2x plus 1, dx. So now this is going to become half x plus, x minus, plus sine 2x over 2, and then a constant of integration. So this is going to become half x plus 1/4 sine 2x plus a constant of integration. Okay, now let's do a power of 4. So if I have something like integral of sine power 4x dx. Now sine power 4x is nothing but sine squared x power 2, right? And sine squared x is nothing but 1 minus cos 2x over 2 and power 2, right? And dx, right? So now this becomes what? This becomes 1/4 integral of 1 minus cos 2x power 2. Now, if I expand it, this is going to become 1/4 integral of 1 minus 2 cos 2x plus cos squared 2x dx. And now, it's fairly easy. This is going to become 1/4 of x minus 1/8 or 1/2, because 2 multiplies by half by fourth in order to get 1/2. And integral of cos 2x is sine 2x over 2. So sine 2x over 2 becomes 4. And then integral of cos squared of 2x dx. Now this is not tricky, but it just requires to have some presence of mind. Now cos 2x is 2 cos squared x minus 1. What if I had cos 4x here? Then this x would be double, right? Double angle identity. So this becomes 2 cos squared 2x minus 1, right? As simple as that. So now this becomes 1 plus cos 4x upon 2 is equal to cos squared 2x, which was the requirement here. So this is going to become 1 upon 4x minus 1 upon 4 sine 2x. And now this is going to become the integral plus half. The integral of half is from here, right? I take it outside of the integral sign, and this is 1 plus cos 4x dx, right? Now just integrate this last one. I'm going to copy the first two terms down as it is, minus 1 upon 4 sine 2x, and this is going to become plus half x, and integral of cos 4x is sine 4x over 2. So this is going to become 1 upon 8 sine 4x, and then a constant of integration. And that's right here is your answer for the integral of sine to the power of 4x, right? So it is as simple as that. So the lesson is that whenever the powers are even, the reduction identities usually come before substitution. Okay, the reduction identities, which are the double angle formulas. Now I'm going to start with trigonometric integration decision table, right? So if you have, for example, sine to the power of mx times cos to the power of nx, make this decision. If the sine power is odd, save one sine. So if this power is odd, if m is odd, then you save one sine and convert the remaining sine powers using 1 minus sine squared x, right? So let's say m was 9. So you will write it as sine x times sine 8x, and sine 8x will be written as sine squared x power 4, right? And then 1 sine squared x will be written as 1 minus cos squared x, and this is cos power whatever. Let's say n is 1000. Who cares? So this becomes u, and then this becomes, so this becomes du upon minus sine x, and this gets cancelled. Sorry, sine x. This and this gets cancelled. This becomes 1 minus u squared power 4 cos, and this is u power 1000 whatever, and this is du, and there's an integral sign, right? So it is as simple as that. Now if the cosine power is odd, okay, let's not remove it. So if the cosine power is odd, then you save one cos. That's it, right? So and convert the remaining cos squared x as 1 minus sine squared x. So the method is the same, and then then you make the substitution u is equal to sine x. Now what if both powers are even? Then you use double angle identities. That is far more useful than trying random substitution. So for example, if this was cos 4x and this was sine squared x dx, so you do know that cos to the power of 4x may be written as cos squared x power 2, and cos squared x will be written as 1 plus cos 2x over 2 power 2. And then there's a sine squared x will be written as what? It will be written as cos 1 minus cos 2x over 2, right? And then you're going to expand it. You're going to first expand this one. So this is going to become so this was a 2. So you take this outside and you also take this outside. So this becomes 1 upon 8. This becomes 4 because it gets squared. So now you have 1 plus cosine of 2x whole squared times 1 minus cosine of 2x, right? So this becomes 1 plus 2 cos 2x plus cos squared 2x times 1 minus cos 2x dx 1 upon 8. Let's do it further. So this is quite complicated. Now you start multiplying. So this is 1 minus cos 2x plus 2 cos 2x minus 2 cos squared 2x plus cos squared 2x, and then eventually minus cos power 3 2x minus cos power 3 2x dx. Let's try to solve it. Simplify it. So this 1/8 comes here, and now let me simplify. So minus cos 2x plus cos 2x becomes 1 plus cos 2x minus 2 cos squared plus cos squared 2x becomes minus cos squared 2x, and this becomes minus cos cubed 2x, right? Very simple. And then this is this. So 1/8 1 plus cosine of 2x. Now cos squared 2x becomes minus 1 plus cos 4x over 2, and cos to the power of 3 2x. Now this is an odd power, right? So you are going to convert it. This becomes cos 2x times cos squared 2x. And then finally there's a dx, and you are going to deal it in the same manner, right? This is quite complicated, quite lengthy, but this is how you're going to do it. Now, okay, so before moving on to inverse trigonometric functions, let's try to just deal with it once and for all. So this is 1 plus cosine of 2x minus half. So minus half is just going to turn this into a half, so I'm going to get rid of it, and this becomes minus cosine 4x upon 2. Cosine 4x upon 2, I leave it as it is. And then there's a minus. Okay, let's do this separately, and then let's deal with this separately. Cos 2x, and then cos squared 2x is going to become 1 minus sine squared of 2x. And then you make the substitution. U is equal to sine squared of 2x. Now this is fairly simple. This is nothing but 1 upon 8 times half x plus sine 2x over 2. And this becomes minus sine 4x over 8. And this becomes minus 1 upon 8. And this I'm going to apply the substitution. So let's use another color. So U is equal to sine 2x. So du over dx is going to become cos 2x over 2. So this becomes, so cos 2x over 2. So just write down cos 2x over 2 as it is. Cos 2x as it is, and this is 1 minus u squared, and dx is going to become du over cos 2x over 2. Du over cos 2x over 2. So I'm going to put a 2 here. This gets cancelled. So 2 cancels this. This is 1 upon 4. And now this is fairly easy. So this becomes 1 upon 16x. This becomes 1 upon 16 sine 2x. And this becomes minus 1 upon 64 sine 4x. And this is minus 1 upon 4 and you integrate 1 minus u squared, so this becomes u minus 1/3 of u cubed, and then a plus c. And u you already know is sine 2x, so I'm going to just write down the final answer. So that's going to become 1 upon 16 of x plus 1 upon 16 of sine 2x minus 1 upon 64 of sine 4x minus 1 upon 4 u was sine 2x, minus 1 upon 4 sine 2x, and plus 1 upon 12 u cubed, u is sine 2x, so sine cubed 2x, and a constant of integration, and that's your final answer, right? So if such a question comes, pray not. So if such a question comes, then you are going to deal it in this manner. Do all so that's going to engage, or that's going to make use of all your knowledge of trigonometric integration, right, and all the substitutions, etc. Okay, so now once we have dealt with this impossible looking integration, trigonometric integration question, let's move on to inverse tangent integration. Okay, we did touch upon it. We also did some derivation of it. Now, so this is part C, inverse trigonometry. We are already 50 minutes into the lecture, but that's fine. Inverse tangent integration. Now, let's say you had to find the differential of tan inverse of x. We saw how to do it. Let's say that u is equal to tan inverse of x. So so tan u is equal to x, and now do implicit differentiation with respect to x. If I apply the differential operator to both the sides with respect to x, so this is going to become sec square u du by dx, and this becomes 1. Okay, now so du by dx is going to become 1 upon sec square u, or 1 upon 1 plus tan squared u. Now tan squared u is nothing but x squared, so I'm going to put 1 upon 1 plus x squared, and du over dx is nothing but d upon dx of u. U was what? U was tan inverse of x, as we saw here. So I'm going to put d upon dx of tan inverse of x, right? And that's how you come up with this, that the differential of tan inverse of x is 1 upon 1 plus x squared. Now, if I apply the integral operator on both the sides and put a dx, so integral of this is going to become tan inverse of x is going to be the integral of, so antiderivative, right? So this is simple. This is not logarithmic, because a logarithm appears when the numerator is the derivative of the denominator. So the derivative of the denominator is 2x. However, this is just 1, right? So you can't do that. So so there was no x, right? Instead, we recognized the derivative, and we also did the derivation here, which we also did in our lecture on Friday last week. Therefore, the integral of this is tan inverse of x and plus c. This is important. It's a family of curves. Now, a general inverse trigonometric form is, so if you have 1 upon a squared plus x squared, right, dx. So you convert it into 1 upon a squared, you take it common, so you get 1 upon 1 plus x upon a whole squared dx, right? Now, if I take, so this becomes 1 upon a squared, and now this is going to become tan inverse of x upon a, and you multiply it by a, and then plus c. And why do you multiply it by a? I'm going to show you. Now see, so this is going to become, okay, just forget about it. Let's do the derivation for this one as well. So now this is 1 upon a squared integral of, now we don't have an x here which we did the derivation for, so let's take this, u is equal to x upon a. So du by dx is going to be equal to 1 upon a, or dx is going to be equal to a du, right? So now this becomes 1 upon 1 plus u squared, which is our desired form, and dx is going to become a times du. Since a is a constant, I can bring this here, so I can remove it from here, and there's an a here, this cancels this, so I'm left with 1 upon a here, right? So 1 upon a, integral of this we already know is nothing but tan inverse of u and plus c, and u is what? X upon a. So instead of u, I'm going to write x upon a, right? So this is the general form for the integration of 1 upon a squared plus x squared, right? Now, so if you are given to integrate, let me change color, 1 upon x squared plus 16, you know that 16 is the squared for 4. So the answer is going to be 1 upon 4 tan inverse of x upon 4 and plus c. That's it. Now, what if instead I give you 1 upon x squared minus 6x plus 13 dx? Now, you will see that you cannot break it in partial fractions, you cannot break it into any other form, but yeah, you can turn it into a completed square form. So this becomes x minus 3 whole square minus 9 plus 13 is plus 4. So now I have something like integral of 1 upon x minus 3 whole square plus 2 squared dx. So now this is 2, or I can turn it into 1 upon 4 integral of 1 upon 1 plus x minus 3 over 2 whole square, right? This is this is just basic algebra, right? And you can see, you can expand it and you will see that, okay, let me show you how I did it. So let's not skip steps. So let's take 4 common. So this is going to become 1 upon 4, and this becomes 1 plus x minus 3 whole square upon 4, and 4 may be written as 2 squared, and since both the powers of 2, I can take it inside of it. So this becomes x minus 3 upon 2 whole squared, and there's a dx. Now when I integrate it, this simply becomes 1 upon 4 tan inverse. So so this is going to become 1 upon 4 tan inverse, sorry, this is, yeah. Now you can make the substitution. This becomes 1 upon 1 plus u squared. So u is nothing but x minus 3 upon 2. So du by dx is going to be equal to half, or dx is going to be equal to 2u. So 2 cancels this. So this becomes 1 upon 2, and integral of this is nothing but tan inverse of u, and u was x minus 3 upon 2, and that's your answer, plus c. Okay, so it is as simple as that. The difficult step here was not really integration, it was recognizing that this quadratic could be it needed completing, right? Now if you have, okay, let me change the color. This is another question. Now this is a very P3 type question. So if you have x squared minus 4x plus 8 in the denominator and an x in the numerator, now you still do not have something similar to the derivative of denominator in the numerator, because the derivative of this is 2x minus 4, right? So how can I rewrite this x in terms of 2x minus 4? So if there's a 2x minus 4, if I have it, I'm going to have x minus 2. So minus 2 is not needed, so I will write plus 2 as well, right? So this x may be rewritten as half of, or I will write down separately. So this may be rewritten as half of 2x minus 4 plus 2 over x squared minus 2x plus 8, and then there's a dx. Okay, now let's see. So this step, I'm going to now separate it by this plus sign right here. So this is going to become integral of half. So I can take half outside, and this is 2x minus 4 over the denominator, which is x squared minus 2x plus 8, and then there's a dx, and then I separate it again. So this is plus integral of 2 upon x squared minus 2x plus 8, right? And then there's a dx. Now this one is logarithmic. The derivative of the, so this is in this form, f of x, in the numerator there is a derivative. So the integral of this is nothing but ln f of x, which we did in the first lesson on Friday last week. So this is going to become half ln x squared minus 2x plus 8, and this is nothing but 4 times 2, right? So let me use another page. So this is plus twice of 1 upon this. I can rewrite it as x minus 1 whole square. Is this minus 1? Yeah, x minus 1 whole squared. So minus 1 plus 8. What is that going to be? Oh, this is not, oh sorry, my bad. This is not 2x, this was 4x. This was 4. So this is also 4, and this is also 4. This is why I was getting confused. This is a 4. Yeah, okay. So this becomes x minus 2 whole square, and minus 4 plus 8 is going to be plus 4, which is nothing but plus 2 squared dx. Now, so we already have the first integral, which is half of ln x squared minus 4x plus 8, and then plus twice of. Now let's do the integral of this. So this is nothing but integral of 1 upon, okay, I can take 4 common again. So this becomes 1 plus x minus 2 over 2 whole square dx. Now u is equal to x minus 2 over 2, and du by dx is just half. So I can rewrite it as 1 half ln x squared minus 4x plus 8, and then plus half, and this becomes tan inverse of this x minus 2 over 2, and dx was substituted by du, 2 du, so 2 is going to cancel here. So I'm just going to have a 2 because this already consumed my du in integration, right? So 2 is going to cancel this, and then there's going to be a plus c. So this is going to be the answer, half ln x squared minus 4x plus 8. And I would recommend that you guys do not watch this entire lecture in one go. Break it into integration by parts, do the exercise, and then come back to this integration by the integration of inverse trigonometry, right? Because we are already 60 minutes into the lecture, and these are quite lengthy topics. Now, this was a proper P3 integration question because it combined recognition, rearrangement, and also it combined the completing the square form. Now, the last part in the calculus series and for the integration as well, which is again part of calculus only, let's do a combined style trigonometric integral. Now, I mean, I'm not going to do it. You're just going to apply the limit sine power 5x dx. Now, so this is sine x, this is 1 minus cos squared x, which is sine squared x, and there's a 2 in this, and this is pi by 2. The limit is from 0 to pi by 2, and now I can make the substitution. U is equal to cos x, so du by dx is going to be minus sine of x. So I'm going to have 1 minus u squared power 2, and sine x is going to cancel with negative sine x, and I'm going to have a negative here, and there's going to be a du, and I'm going to use the x limit only. I'm going to convert it back into x form, right? So now this becomes minus 1 plus 2u squared minus u power 4, an integral of that, and there's a du. Now let's integrate it quickly and then apply the x limits. X is equal to 2 to x is equal to pi by 2. Now this is going to become minus u plus 2/3 u cubed minus 1/5 u5, and now we are going to apply the limits. X is equal to pi by 2 and x is equal to 0, but before that I must put the substitution back. So this is going to become minus u is u was equal to cosine of x, right? So this is minus cosine x plus 2/3 cosine cube x minus 1/5 cosine 5x, and the limit is from pi by 2 to 0. Now cos of pi by 2 is nothing but 90, so is 0. So the first thing is 0. Again, cos of pi by 2 again is 0. So 0 times 0 cubed is 0. 0 times 2 by 3 is 0. And again, this is 1 upon 5 times 0. So there is nothing here. Now, cos of 0 is 1. So there is a minus 1. Cos of 0 is 1. 1 cubed plus 2 upon 3 is plus 2 upon 3. And then minus 1 upon 5. Now this whole thing may be ignored. There's a minus sign here. So 2 upon 3 minus 1 is minus 1 upon 3 minus 1 upon 3 minus 1 upon 5. Minus 1/3 minus 1 upon 5 is nothing but 1/3 plus 1 upon 5. So 15, 5 plus 3 is nothing but 8 upon 5 squared units. And that's your answer, right? It is as simple as that. Now, notice that definite trigonometric integrals often simplify dramatically because of exact values at a or pi by 2 or pi and related angles. Now, I want you guys to stop here, do more questions on these integration by parts and mixed trigonometric integrals from your book, and then come to trapezium rule, which is also the numerical integration, right? Now, what if you have a function something like e to the power of sine x times ln x over x squared? Now you cannot integrate it, right? So once you cannot do it, you can find function values. For example, this was equal to y. So let's say that this is some impossible looking function like this. Okay, now in such a case, if you were to integrate it from the limits a x is equal to a to x is equal to b, now you cannot do it. The first part, maybe the first technique in order to find out this entire area would be to form a rectangle here or a rectangle here or maybe a rectangle right in the middle in order to cancel this over and under recording, right? However, the best approach, or you could maybe find out this area, but again this part would be recorded. So what I told you was, integration is the summation of these thin strips, right? Now you cannot do infinitely many, but what you can do is you can convert it into maybe 4 intervals, 1 2 3 4, but it has to be equal intervals, right? You call it h, you call it h, you call it h, you call it h, and what's going to be the width of this h? It's going to be a minus b upon 4, right? Because there are 4 intervals, right? So h is going to be equal to h is going to be equal to b minus a upon 4 if there's got to be 4 intervals, 1 2 3 4, right? Now I want you guys to draw it as well in order to anchor this concept or solidify it in your heads. Now, so you will see something. Let's say that this function is f of x. You will see that this value is going to be equal to f of x plus h, a plus h, sorry. If this is a and this is h, so this is going to be a plus h. This is going to be a plus 2h. So this is going to be function value a plus 2h. This is going to be equal to function value is going to be equal to, so if this is a plus 3h, this is going to be function of a plus 3h. And this value right here is going to be equal to function of a plus 4h. Now you will see something. If I join this, so I see a trapezium half into height, which is this, into sum of parallel sides, this plus this. So sum of sides is f of a plus f of a plus h. Now the second one is going to be half into height into sum of parallel sides. Now this side is a plus h and this side is a plus 2h. So I'm going to write down f of a plus h plus f of a plus 2h, right? And then the third interval is going to be similar into this one and the third one, right? A plus 2h plus a plus 3h. And then the last interval is going to be half into height into a plus 3h, f a plus 3h plus f of a plus 4h. Now, if I just take common, I can see that this is common. So I can take this all common, half into height into. Now I can see that this one is once and this one is once. However, this is twice. And I also can see that this is twice. And I also can see that this is twice. The endpoints is just counted once. So f of a plus f of a plus 4h, the last y value. And all the rest of them is counted twice. So f of a plus 2h plus f of a plus 3h. So this is your trapezium rule formula. That's it. There is nothing else to it. Okay. So if there are n intervals, so just to give you a general form, I mean this is the easiest topic in integration. So if the interval from a to b is divided into n intervals, and these are the limits, x is equal to a and x is equal to b. So you know that h is going to be equal to b minus a upon n, right? And so the coordinates are going to be equal to so the first coordinate is going to be equal to y naught, the last coordinate is going to be equal to yn, and all the rest of them will be equal to 2 twice of y1 plus y2 all the way to yn minus 1, right? And yn is going to be counted once, right? And half into height is this, b minus a upon n, b minus a upon n, right? And that's it. So this is it. The first and last ordinates appear once. Every internal ordinate appears twice, y1, y2, yn minus 1. That pattern comes from adding neighboring trapeziums, right? Now, so let's say, so you will apply this if you're doing e minus x squared between 0 and 2. Let's say that you are doing it in 4 equal intervals between 0 and 2, right? So this is the first, this is the so at 1 upon 2, and this is at 1, and this is 3 upon 2, and this is 2, right? So your age is going to be equal to half. So area is going to be equal to half into height is half, into sum of parallel sides. So this one, e to the power of minus 0 squared, is going to be counted once. This ordinate, the y value, is going to be counted once. Minus 2 squared is going to be counted once. And all the rest of them, this are going to be counted twice, right? So this one is going to be e to the power minus half squared plus e to the power of minus 1 squared plus e to the power of minus 3 upon 2 squared, right? Now, so this looks pretty, so do not just see what I'm writing, also hear what I'm saying. So this 1 upon 2 times 1 upon 2 is 1 upon 4. And e to the power of minus 0 squared is 0, 0 times minus 1 is 0, e to the power of 0 is 1. Now, 2 squared is 4, 4 into, now this squared is on 2, not on minus, right? So 2 squared is 4, 4 minus 1, so this becomes 1 upon e4, and okay, and then plus twice of this thing. So this one is half, so e to the power of minus 1 upon 4, or 1 upon e to the power of 1 upon 4. This is e to the power of minus 1 or plus 1 upon e, and this is e to the power of minus 9 upon 4 or e to the power of 1 upon e to the power of 9 upon 4, right? And that's going to give you an answer, right? And that's it. So approximately this is going to give you, if I can put it in my calculator, I just did it, this is approximately going to be 0.881 correct to 3 decimal places. Now, the errors that students make is that they confuse intervals and ordinates, right? And if there are n intervals, so if there are n intervals 1, 2, 3, 4, ordinates are going to be 5, 1, 2, 3, 4, 5, right? Now you calculate h incorrectly. H is going to be b minus a upon number of intervals 1, 2, 3, 4 upon 4. That's going to be h, which is the height of these trapeziums, right? You double the n values. Don't double this value and this value. This is just counted once. This is just counted once. All these values, f of a plus h, f of a plus 2h, f of a plus 3h, they are counted twice. Okay? You round too early. So what if you were rounding this and rounding this and rounding this and rounding this, and eventually this answer is not going to be as precise. So I kept it all in the exponential form, and towards the end I put it all in the calculator and got something very, very close to the exact answer, right? Now, You ignore the radians. When the function contains trigonometry, the calculator must actually be in radians for P3 calculus. So for example, if you were doing sine of x squared, I don't know, ex or whatever, and this is between 0 and pi by 2, I don't know, something like that, then whenever you're calculating it, the function values, you must put your calculator in the radians mode. Now, about overestimate and underestimate. If your curve goes like this, if the exponential curve has positive powers and is going like this, then definitely when you are breaking it into trapeziums, it's over calculating, right? This is the overestimation. This is the overestimation. However, if if your curve is going like this, something like this, so now it's underestimation. So you are underestimating, right? You're ignoring this part. You're not really ignoring this part, but you do not have the way of doing it, right? So students memorize that trapezium rule gives an overestimate or an underestimate that is followed. It depends on the shape of the curve. The rule replaces each curved section with a straight chord, right? So this was a curve, but you put a straight chord here. This was a curve, but you put a straight chord here, and hence it was getting underestimated, right? So now, if the curve lies above the chord, like in this case, then there is underestimation. If the curve lies under the chord, then there is overestimation because you are overestimating it. The curve was here, right? So the estimate is an overestimate because the straight line segments join successive points lie above the curve in this case, okay? That is much better than only writing overestimate. Now, so you may get something like this in your exam, 1 plus x cube. I'm not going to solve it. X cube dx between 0 and 1.5, and you are going to take 3 intervals, right? So between 0 and 1.5, the h is going to be half, right? And then you are going to do it, leave your answer. I will check, and you can check the answer. This must, I solved it, this must be equal to 2.01 squared units. If you're getting the right answer, comment your answer in the comment section. Now, how to choose the method in the exam? Let's put the whole chapter together. When you see an integral, do not begin calculating immediately. Run this sequence. Can I use a standard result directly? If this is, so this is simply power rule, reversal of that. If so, this is simply the chain rule, reversal of that, right? Or apply substitution. Similarly, apply substitution here, apply substitution at cosine of ax, right? So do all of that. Now, if you have something like x to the power of x squared plus 1, 5, so this is the sort of the derivative of the inner function. So substitution is what you need to do. Now, here you are not doing substitution directly, but the result that you get is a form of substitution, right? So there is a so you can introduce a and a here. So now there is a constant available here, right? The derivative of the inner function. Now, if you have something like this, or x sine x, we spent considerable time here in these questions in this lecture. So you have to apply by parts. Now, is it a rational function? Then you will check whether you need algebraic division, partial fractions. So maybe you have something like 1 upon x plus 1, 2x minus 3 dx, and maybe it is not in this form. You have to first factorize it and then find it in this form. So break it partially, and then you can apply logarithmic integration. Or if you cannot make the factors, then turn it into a completed square form, or see if inverse tangent is what you need to do. Now, you have to also ask yourself, does it involve powers of sine and cosine? Then you have to see whether the powers are odd or even or both, right? In which case you will have to use the trigonometric identities for double angle formula. Now, you also have to see whether Cambridge is asking for an estimate, in which case you have to do numerical integration for the impossible functions which are not integrable, right? Then you have to apply the trapezium rule, which we just did. So I am going to leave you with some questions, and I want you to do practice 1 plus x squared 7 dx, and then question number 2 would be x cos 3x, which we just did in class, question numbers in this lecture only. And then I also want you to do this sine cube x cos square x. If you did the lecture, you should know or understand it. You should know how to do it. And let's do 1 upon x squared plus 8x plus 20 Very easy. Should be able to, so this should be inverse trigonometric, and also estimate fx dx, right? So between a and b for n number of intervals, right? So tell me how you're going to do it. This is a proper trapezium rule. Now this completes our main P3 integration sequence. So 9709 slash 32 main, the largest, the beefiest chapter has been done. You should now be able to recognize direct integration, which is the reversal of power rule, the substitution, integration by parts, logarithmic forms, inverse tangent forms, odd and even trigonometric powers, definite integrals, area questions, and numerical integration using the trapezium rule and the overestimation and underestimation criteria. The most important skill is not carrying out the method, that's easy. It is choosing the method. Which method must you choose? In an exam, the first 10 seconds should be spent identifying the structure. 10 seconds in identification. Only then should the pen begin moving. Because in P3 integration, most students do not lose marks because they cannot integrate. They lose marks because they begin with the wrong idea. So that concludes the chapter. If you benefited from this video, subscribe to the channel, like this video, leave comments. If you need any help, you can reach out to me on my WhatsApp +92 329 3028 485. If you have any suggestions, leave that in the comments or in our direct message on Instagram. On Instagram, we go by the same handle, EASY easy TALEEM Taleem. Okay. So this lecture was the lengthiest. It's 1 hour 20 minutes, but hopefully this is covering 3 weeks of what you study in a class. So also this lecture alone is not going to do any good to you. Make sure that you're complementing it by practicing the exercises from the respective chapters in your Cambridge Indoors Black Book. If you don't have, you can reach out to me on my WhatsApp and I will share the digital copy with you. So for a lot of good stuff on Instagram, follow us there, because I regularly post carousels and challenge stories, etc. So it's going to do you good if you're doing that. And now I'm going to see you on Wednesday with our numerical methods chapter. So now we just have four chapters left. Numerical methods, which is just going to take one lecture. Then we are going to spend 1 day on differential equations. We are going to do 2 days on vectors and approximately 2 to 3 classes on complex numbers. So by the 21st of August, I'm planning to inshallah conclude, by the 7th of August, 7th of August, inshallah, I'm going to conclude 9709 slash 32, and then we will move on to the S2 lectures. I'll see you guys in the next class. Good luck.